So welcome. Today is Wednesday, August 5th, 2020, and this is a NARI SimCenter webinar intended to disseminate educational information and research outcomes around natural hazards and the built environment. For more information about NARI, the Natural Hazards Engineering Research Infrastructure, visit the NARI website at designsafe-ci.org, where you can find links to the SimCenter and the NARI Learning Center. Today's webinar is hosted by the Natural Hazards Engineering Research Infrastructure's Computational Modeling and Simulation Center and Design Safe. This webinar is supported by the National Science Foundation under awards 1612843 and 1520817. Any statements in this webinar are those of the presenter and do not necessarily represent the views of the National Science Foundation. Today, we're joined by Dr. Andrew Winter. He is an applications support engineer for Siemens PLM software. Prior to joining Siemens, Dr. Winter held a postdoctoral scholar position for numerical modeling the wave structure interaction of oscillating wave energy surge energy converters using open foam at the University of Washington, where he received his PhD. The title of his presentation today is The Effects of Flow Shielding and Channeling on Tsunami-Induced Loading of Coastal Structures. And Andrew, I invite you to begin presenting.
Thank you, Matt. Thank you for that introduction. As Matt mentioned, today I'm going to talk about work related to what I did for my PhD on tsunami loading of coastal structures, and in particular focusing in on sort of a localized community effects where you have structures farther offshore redirecting or shielding structures more onshore from incoming tsunami inundations. So you can see here, this is a picture from Japan. There's a bunch of structures still remaining. Most of them, as far as I know, are concrete, reinforced concrete construction. And so structures farther offshore could definitely, cause deviations in the inundation. Whereas a lot of modeling that's done around this is kind of, you consider a bare earth scenario without any structures. So this work was meant to kind of enhance how you could analyze that. So to begin with, here's just kind of a presentation overview. We're going to go through what was the motivation for this work, both in like the tsunami demands and in design codes. What kind of experimental work did we do back in 2017 for this? And what sort of numerical modeling did we do to develop a validated model off of the experimental results? And then finally, we developed what we think is an improved force prediction equation that accounts for these shielding and channeling effects. So to begin with, what is causing tsunamis? I'm sure you all know, Earth's tectonic plates. And in particular, reverse faults are the main culprit of giant subduction zone type earthquakes that cause tsunamis. And 88% of the world's tsunamis are caused by this type of earthquake. The remaining ones are mostly things like subsea landslides or even subaerial landslides coming off of a mountain down into a lake, usually. But most of these occur in the Pacific Ocean, which is of concern to us where we live on the West Coast at University of Washington. And homing in more on that, the Cascadia subduction zone here, which stretches from Vancouver down to California, is the big issue in terms of, potentially causing a future tsunami. As research shows, every roughly, between 500 and 600 years, a giant magnitude 9 level kind of earthquake should occur that would cause a disastrous tsunami. And so since this fault takes so long to repeat causing an earthquake that's the level that could cause a huge tsunami, as this process is going on, the zone becomes locked, which geologists are measuring all the time how much of it is locked as best they can. And as this locking occurs further and further, the friction causes deformation and stress buildup in the plates of the earth. Eventually it slips and gives way, or maybe some partial fracturing of plate stuff on the interface. And finally, since the water is displaced, it's going to move outward from there as a tsunami, perpendicular to the fault. And at the ends, you get kind of more fringe, radial, circular propagation that's not as bad. In terms of what this can do to communities, these are some examples I have here from 2004 and 2011. You can see on the left tsunamis in conditions like this, where it's not such an urban environment. They completely wipe the map clean of all vegetation, and they ravage the coastline and completely change its profile. Also, lots of seawater is left behind on what could possibly be arable land, so it's hard to use, and just all the small structures are completely wiped down or wiped off the face of the earth there. And also in Japan here, you can see in the harbor here, only a few of the larger or more strong reinforced concrete type structures have remained. All of the other small, either timber or light frame type steel structures have been completely knocked down by the inundation. And so what we're aiming to understand, as I mentioned before, is, you know, maybe a small building that wouldn't withstand the tsunami on its own is behind one of these big buildings on the front of the coastline there, and it could survive if designed adequately for those loads. So some people have studied this before. It is in ASCE 7 as of the last release of that in 7.16. However, the force amplifications provided there are not a part of the main code. They're in the commentary, so this is not, you know, required for your design. The other thing is there's no treatment of shielding effects. In other words, you know, one structure kind of hidden behind the other, like I was just mentioning. So that would cause a force reduction that could be very valuable to, you know, assessing whether your structure is going to still be there or not. And channeling effects are considered in the code, but they only consider very symmetric configurations of structures in both of the configurations that were tested. You can see here on the bottom left, these little blocks in the yellow boxes are completely perfectly on some grid, symmetrically spaced away from the test structure further on shore to the left there in the purple box. And the same thing in the top right. You can see two symmetric flow blockages were channeling the wave in towards a central structure. So the things we aimed to do in our experiments were go beyond the perfect symmetry conditions and also consider shielded conditions to come up with a very overall comprehensive design equation based off of numerical model parametric study results. So diving into the experiments that we did, we wanted to determine flow shielding and channeling effects from our experimental data. And so we went down to Oregon State's Large Wave Flume in the Hinsdale Wave Research Lab. And here we used a test structure that was actually borrowed from a previous experiment, but it's a steel box that has a reinforced frame inside. So even though it's like a reasonably thick steel gauge plate on the wall, the frame makes sure that it's more rigid. So you're getting like a sort of a fixed structure response more than a very flexible one. And we had an array of locations where we placed pressure gauges in little taps along the sides of the structure. Also above, there was this fancy looking support frame that spanned the flume channel as kind of like a bridge, and it was the overall top part here that you can see with my mouse, this part connected to the walls, and this bottom part here in the middle allowed translation in the wave propagation direction. And there's two sets of these frictionless slider bearings, so you can have translation either in the streamwise wave direction or in the transverse along shore direction. So hopefully we're isolating out just the loads in those directions, you know, barring whatever kind of friction is actually in there with since realistically there has to be some. And you can see here our profile for our experiments. We had a two-slope beach coming up to a flat ground area, and the structure was supported on legs, which later in numerical modeling we ignored for simplicity's sake to not make the mesh have to be too tiny in too many places. but we'll talk more about that later. The other thing is our measurement gauges that we used. We used acoustic Doppler velocimeters to get the velocity field of the wave coming in. We also measured the free surface elevation with ultrasonic wave gauges and traditional wire wave gauges as well along the length of the flume and surrounding the test structure. And all of these were used for numerical model validation later. And you can see here, this is where they're placed. They're placed surrounding the structure. And the pressure gauges were concentrated mostly on the front of the structure because we were concerned about the wave impact in the streamwise direction, initially on the front of the structure, but we also placed gauges on the sides, the bottom, and the back to assess any kind of twisting that might occur from an asymmetric loading on the left or the right, uplift on the bottom, and a resisting force on the back from water back there. Also, so you can see inside all of the wires coming in through here to the top to all of our gauges and our load cells. We did have leg load cells to measure loads on a couple of the legs, but they were so insignificant compared to the total load, we didn't really use those results. We used the net streamwise force, which you can see was measured here by the back load cell. And then we had 2 load cells on the side attached to part of the frame on the right side. And also we had 4 vertical load cells attached to the roof of the structure, so you could get you can measure overturning and twisting in any direction as well as the vertical force. And these are just showing where they are in the experiment. So you can see those transverse ones in the green box are not directly attached to the structure, they're attached to the piece of the frame that would be moving in that direction that the structure is attached to. We tested 3 wave types in total, but we neglected one of them because it was breaking right on the front of the test structure, and it seemed highly unlikely that that would ever happen in a real tsunami situation. So we stuck to mostly testing these 2 waves, an unbroken wave and a broken wave, which are kind of maximizing different aspects of what the wave maker is capable of in the Hinsdale Wave Research Lab. The first one, the unbroken wave, you're getting the maximum piston strokes, you're getting the longest duration of inundation. Whereas the other one, the broken wave that we created, had reached the max velocity of the piston wave maker, but we were not able to hit the maximum paddle displacement due to the physical constraints of the wave maker. We didn't want to break it. And so here's an example of what these looked like in the lab. This is the unbroken wave coming in, and yes, it is actually moving. This is a very slow-mo video. You can see it's rising up this is one of our tests with an obstruction, which were concrete blocks. I'll talk more about that later, but there's one on the right. Now the wave is coming in up on the test structure. And so this is a very smooth wave impact. It's not such a turbulent, slamming type of an impact. It's more of a smooth rise up the structure. And so these demands were much less than for the broken wave. And moving on to the broken wave, this one is going to come in as a fully broken bore already. The wave is broken halfway between the wave maker and the test structure to ensure that it's like a broken tsunami bore. Let's see, it should be coming in the bottom here any moment. Apologize for my colleague not hitting record later. Here we go. So you can see here comes in the big frothy broken wave, and this caused a huge slamming load and lots of splashing, which ended up being problematic for our ultrasonic wave gauges, which you can see my mouse is right here, and the splash definitely douses it. So we'll talk more about that later in terms of how that came out for our free surface measurements, but yeah, so that's that wave. So to discuss the configurations that we did do some symmetric configurations, but we also tried to have some asymmetric configurations, and also to vary the level of blockage of the structure as well. So you can see we did like a base case with no neighboring structures, this was case A, and then asymmetric cases we had were case B and F here. The wave is going to get kind of redirected at an angle a little bit away from the structure that it impacts first, the concrete block. So it's not going to hit head on the test structure as much as it normally would. The other thing is you can see cases B, C, and D give different levels of blockage of the flow channel. And case E would be like a perfectly channeled case. So case E, you should expect to match ASCE results very well. Same with case B, since it's not actually shielding the structure, but cases F, D, and C, where there is at least some shielding, if not full shielding of the structure, you're going to expect to see a much different result than what the code is going to predict. The other thing is we tried to validate between our gauges to make sure that the load cells and the pressure gauges weren't lying to us. And so the gray curves here are sort of all of the tests showing sort of the experimental range of variability. But the purple curve is the mean load cell value for the one streamwise load cell that measured the wave impact. And the green is the integration of the front and the back pressure gauges to determine a force on the structure in the same direction, and that compares quite well. So I think our gauges did a good job. The other thing is we then did regressions of the pressure field data to figure out these surfaces, which these were used to calculate the force. And you can see here, I apologize, one thing that's a little confusing is each of the images of the test structure, the orange block, and the gray, the concrete blocks, the horizontal or transverse y-axis in each of these figures is flipped from what that should be. So for instance, case F, you're like, why is the value really high on the right side? It looks like it should be higher on the left side where there's no blockage. That is true, it should be flipped. So this was just a relic of past figure making. But you can see all of the cases that have shielding like D, C, and F definitely cause very large reductions in the localized pressure field. But you also get things like in case F, where the channel between the two structures closely placed causes a very large increased velocity, and you get a very locally huge pressure field compared to the base pressure field, like if you look at case A. So we were trying to capture all of these effects, amplifications in pressures and forces due to channeling, and reductions due to shielding. The other thing we looked at here was our velocimeters, and you can see in a lot of these cases, it's a little difficult to assess comparing between case A and the other cases, because case E, for instance, here, if you look, you'd think gauge 3 and gauge 4 should have identical results. However, these results fluctuate a lot in time due to the turbulent nature of the flow. So capturing at an exact same instant they look the same is difficult. However, this was taken, all of them are at the maximum streamwise force of gauge 4. So that's what we're comparing here. Is you're looking at gauge 4 in case A versus all the other ones. And so you can see in a number of these cases where there is some channeling due to the neighboring structure, for instance, case C and case B, you could compare to case A very readily and see that the broken wave velocity, which is the one of interest since it's the most like a tsunami, definitely got much larger. So not only did the forces and pressures experience amplifications, you can see it very directly coming from the velocities as well, which makes sense since the dynamic pressure depends on the square of the velocity. And getting into what the code says about this, this was some research by Nuri in 2010 from University of Ottawa. I believe that was one of the experiments cited way back earlier in the slides. And they developed this curve here that tells you a force increase ratio based on how much the channel is blocked. But they also placed a bunch of restrictions on the distances between things in the configuration. For instance, you have to have a large enough separation L between your structure on the right there and the channel on the left. Also, there is a restriction on the range in which you can have the blockage ratio exist between 0.2 and 0.4, which also doesn't seem as widely applicable as you would like it to be for a design equation. So we attempted to expand beyond that. But just comparing the experimental results alone, you see, as I was mentioning, the unshielded cases, B and E, right? There's no gray concrete block directly in front of the orange structure. Those ones performed exactly as you would expect according to the ASCE results, whereas anything with shielding at all, C, D, or F, they're drastically reduced in terms of their ratio of, you know, their force versus the case without any blockage. So this is what we're attempting to capture in our equation eventually. And also, by doing that, we're going to expand the range in which our equation is applicable. We attempted to do a much wider range of distances, so very close structure patterns and very separated structure patterns, so you can have a very widely applicable result. So just kind of the conclusions of this, you get greater than 50% reduction in force for only 50% shielding of the front face of a structure. And in the channeling, more or less, you just get increases due to higher velocities due to a Venturi-like effect between pairs of structures or between the wall of the flume and a structure. The other thing to note, though, is even if you get a channeled velocity like that's higher and could cause a higher force, it needs to be more directly aligned with the structure. For instance, here, case E has a larger force than case F by far, because case F may have channeling and it may have a higher velocity than E even, but it's not directly aligned with the orange structure, so you're not going to get the full impact on the structure. Yeah, and as I mentioned, good comparison to ASCE 7 for channeled cases, but not for shielded. So after we did all this, we wanted to develop a numerical model that we could use for parametric studies that would expand beyond the range of conditions, so we could develop a force equation that was very widely applicable. And for this work, we chose to use a 3D Reynolds average Navier-Stokes CFD solver code and try and replicate our measured tsunami loads and free surface elevations as accurately as we could. And so we used the OpenFOAM software library for this, and it's a finite volume method-based solver using the volume of fluid method for free surface tracking. So it's a two-phase air-water type model. Additionally, on top of OpenFOAM, I used Pablo Aguera, who I believe he's at University of Auckland now, I want to say. But he was from IH Cantabria in Spain, and he developed during his PhD this Olaflow package, which is basically a coastal engineering add-on to OpenFOAM. And that allowed very easy implementation of the wave maker boundary condition that I needed. For turbulence, we settled on using the K-omega shear stress transport model developed by Mentor in, I think, '92 for its ability to deal with extreme flow separation off of a bluff body like this box. And we'll talk more about that later. And in terms of like how numerically expensive is this going to be, we used 4.5 million cells per case roughly, and so they weren't that bad. We could run them on about 4 cores with, or four nodes with 16 cores each is what I did all of my jobs on, more or less. The main criteria in terms of setting up a good model that took the vast majority of my effort in my PhD was getting the mesh right. And getting the mesh right involves reducing the non-orthogonality and the skewness of the mesh. So in the bottom right here, you can see that is the worst possible case. You have a difference between the cell edge center and where a vector connecting the cell centers crosses that line. You also don't cross that line perpendicularly, so that's bad. You want it to be like the top left, because all of the finite volume schemes in these codes were derived assuming that this type of condition is what you were working with. They didn't imagine you were going to do these free meshes that were so crazy. And OpenFOAM does have internal correction factors to deal with this, but they're only going to get you so far. You want to avoid this as much as possible. And so to do this, this is my meshing scheme in the flume chopped up into 3 chunks here. So the initial part here, the horizontal dynamic deformation, that's what the Olaflow solver is doing. It's moving the left wall according to the piston wavemaker time history of displacement. And that part of the mesh gets squished. So that's why if you look at the delta X of those cells, it's a bit larger than to the right. So by the time it's done getting squished due to the piston wall motion, it is equivalent to the same size as the ones to the right, outside of the red region. And in terms of refinement, I used uniform grading from the atmosphere and from a lower boundary in the flume up to the free surface to get nice refinement where the wave is going to be passing through, to have good resolution on that. And horizontally, I graded it from the end of the first beach slope towards where the structure is going to be in the purple region, and then expanded it again towards the end of the flume where I don't care about the solution being as refined. I just want to reduce my cell count, since that's after the wave has broken and hit the structure. And initially everything started from 10 centimeter size, and this is about a 100-meter flume roughly. So, and this is just a close-up of what the structure ended up looking like. This is the concrete block in case D right in front of the test structure, just as an example. So it goes all the way to the ground. The test structure behind it does not go all the way to the ground, and I did not model the legs. We did, the proportion of the load on the legs was so minimal compared to the overall structure. We opted to reduce the numerical solver time and complexity of setting up the model by eliminating the legs, since the mesh would have to be so much smaller to conform to their shape. In terms of setup of the model, getting your initial conditions is very important. And in particular, the turbulence modeling of this aspect of setting up the numerical solution was one of the more difficult parts to get right, in addition to the mesh. And I did this by taking experimental measurements that were in the beginning of where the wave was as much as possible. So the first ADV, acoustic Doppler velocimeter, along the length of the flume, took measurements of the velocity histories from there, and then calculated the ensemble averages. That's what the green U, X, and U, Y in the little angle brackets are. And then for turbulence, you care about the fluctuating velocities. So you subtract the mean from the total, and you get the turbulent quantities. And then you can calculate your turbulent kinetic energy, which is just 1/2 times the sum of those squares of the velocity components. And also in most of these models, they're 2-equation models, so you have to have the dissipation rate as well, the epsilon value there. And this is just an equation from turbulence theory, so you plug in your numbers, crunch it out. And finally, for the K omega SST, you need the omega value, the turbulence frequency, which again, calculate that from your equation from theory. The one big assumption in all of this stuff, or two big assumptions, were we neglected the Z velocity due to extremely noisy, erroneous data measured by the ADVs. And also in the initial part of the wave, most of the motion is purely horizontal translation. And you have circular orbital patterns. If you watched the previous webinar by Andrew Kennedy, you would have seen that. So we didn't concern ourselves so much with that. We said, all right, we're going to take these velocities and calculate our turbulence parameters from that. In terms of which model we used, we did do a range of models to test which one gave the best results. And in previous research I had done on bridge structures, the standard K-epsilon model worked very well. But honestly, after doing all of my PhD research, I feel like that was a bit lucky and a fluke, since this model can't handle flow separation well, and it over-predicts the turbulence kinetic energy, the K value, in stagnation regions. So on the front of the structure where the wave is going to impact right in the middle, the K starts to build up and it starts to give erroneous answers. So that's not a good model to use. We also tried the K omega SST and the nonlinear realizable K epsilon models, which are available in OpenFOAM, and they gave very good magnitude results, but the nonlinear realizable one was off in time. And so we selected the K omega SST. The one big disappointment here was this Launder-Rees-Rohde model, which is a Reynolds stress model, which is theoretically more physically correct than any of the others. There are more approximations built into these other three models, which are used. And the difficulty though there is getting the initial conditions correct, and you have to make some assumptions unless you have a lot of measurements that we did not have. And so the assumptions did not work very well. So I would recommend sticking with K omega SST for applications like this. And here's a little sample of what actually OpenFOAM can do for you. So you can see on the left, the wall moves and creates the wave. And this is the broken wave, and it's going to come in, and right about here, it's more or less a fully broken bore, and there's your impact on the structure. And all of these visualizations were created using ParaView, which is also a free software. And here's a close-up from the front. The wave is going to come in just like the video from the experiment earlier, and so you can see very similar result, which makes sense since the forces we got were very similar. And comparing the experiments to the numerical values, in this graph, the green is OpenFOAM, orange is the integration of the pressure gauges, and the purple line is the mean of the load cell values from different trials in these configurations. And the gray are all the different trials of the experimental results, just plotted out to kind of show you the range of experimental variability. And in all of these, the OpenFOAM curve at the peak, which is the main value we care about, we wanted to estimate the maximum impact force as best as possible, is definitely within the gray range of variability, and also comes out quite close, especially in A, B, C, and E, to matching between the numerical and experimental results. And you can see the free surface on the right, looking at the unbroken wave over here as an example, also looks very realistically similar in terms of the elevation it reached on the structure. And as I was mentioning, in terms of free surface elevation, you can see here as the wave is propagating along the flume, OpenFOAM, the green and the purple and gray curves match quite well. And near the structure also matched quite well, but it was much more difficult to compare the experiments to the numerical results due to the splashing that I showed you earlier in the broken wave video. You can see in the front, all of our recordings at that ultrasonic wave gauge were completely corrupted, and the values were like infinity or 0 or -1, things that made no sense. And I tried to salvage some of the results you can see at gauges 2 and 4 and 5. But even though most of them were okay, there's still some erroneous results that messed up calculating the average. Although you can see the green curve fits through the experiments everywhere that those spikes in the data are not occurring. Even behind the test structure at gauge 6, there's quite a good match between OpenFOAM and the experimental result, which I thought was definitely showing that the turbulence model is doing its job. In a flow separated region, things are still coming out pretty accurately. So overall, just as a conclusion here, using the 10 centimeter global cell size was good enough, and reducing it down to 2.5 centimeters. You're not trying to resolve super fine boundary layer results here. To get the net impact force correct, you don't need to go as fine. That would be, I think, one of the big takeaways. And also, out of a lot of the standard turbulence models that you might use on this problem, the K omega SST model was the best option. So for developing our force prediction equation, what did we do? Well, we took this validated model and we just started moving the neighboring structures around in space to get a bunch of results that we could then use to figure out a design equation from for the streamwise force. And so our goal was to vary the location of a neighboring structure here, the gray blocks, relative to the design structure or test structure, the orange box. And so we just chose a wide range of X, Y coordinates here, which are defining the back position of the neighboring structure relative to the design one and the alignment of their center lines. And we assumed initially more complicated forms of a wake shape, but we settled on something that we thought was more amenable to a design code implementation that wouldn't be as hard for engineers to use. There's something that's just a linear shaped wake approximating a true one. And so in this model, the unknowns are the wake length behind the neighboring structure and the width of the wake length at the back of the neighboring structure. So this is what our parametric study results are going to help us do in terms of taking force results and figuring out ratios that you can multiply the size of the neighboring structure by to get the wake width and wake length. That was the goal of this parametric study. And so we have three factors that went into this. On the right here, before I move on, you can see the total force ratio in terms of what you would multiply the base case by with no neighboring structures is the product of three things. One we called the momentum factor, which is kind of trying to account for the blockage reducing the amount of energy that would be able to be transmitted to the design structure. The shielding factor is accounting for how much of the front face of the design structure is blocked. And the channeling factor is kind of thinking back to, like I mentioned, a Venturi effect, where you have a reduced channel causing an increased velocity, so you get an increased dynamic pressure. So that's trying to account for that. And just the product of these three terms would give you something that you can amplify the base case force by. And as I mentioned, we just started moving the neighboring structure around, and these images show you horizontally in the y direction all of the positions we used. And since this is symmetric, we only did 1/2, right? We didn't continue to the right side. There's no need for that. The other thing we did was we considered 11 streamwise positions, as you can see up at the top in the text here. So we had a very large range of results. We had 88 one neighboring structure cases, and we also had 187 more cases where we doubled the flume width to see if the walls were having any effect on the simulation, and it, also on the experimental results being accurate or not. And so what our concern was here, expressed in an image, maybe a little better than my words, is that if you have a neighboring structure near the wall, you're going to get a flow behavior that's not necessarily the true flow behavior around a neighboring structure with no wall over there, right? Because in real life, there wouldn't necessarily be a wall if the neighboring structure is supposed to be the only thing changing the flow. And since there's like a stagnation point at the corner of the neighboring structure and the wall it's touching, it's effectively, in concept, kind of like having a double wide neighboring structure. So we were concerned, how different are the forces going to be if you take away the wall? So we just doubled the flume width to move it far away to the left and the right, and see what would happen to the results, just to test if our results are realistic enough or not. And if you compare them, this is just for the three of the positions from the original experimental configurations. You can see the purple curve is the original flume width of 12 feet, or 24 feet, it's doubled, and the green is the 12 feet, the original. So you can see there's a little bit of a reduction and an amplification in the middle of the flume, but near the wall, there's absolutely no change. It's basically essentially the same value. And so since these were very close, we decided in our parametric study, we would continue with the both of them and develop results using the combined set of data. And to do that, we needed a very large range of high-performance computing resources. And so we used local things at the UW. These HIAC is our HPC cluster there. And so I used 4 different queues within that. And also at TAC, I made very good use of the SKX normal and the normal nodes to do 2 neighboring structures, which the results are not presented in this presentation, but we're currently working on developing, augmenting the design equation to account for 2 or 3 structures. So we ran a lot of different cases. And as you can see, what might be important to you is on TAC, it took 1 to 3 nodes, 2 to 3 days to run these 4.5 million cell cases. I suppose the HIAC is not as relevant, but it was a similar amount of nodes, but slightly longer time. And what did we do with all of this data? Well, like I said, we wanted to get a wake width and a wake length. That was the 2 unknown things in the geometry going back to our configuration of our structure here, right? We didn't know the width and we didn't know the length of the wake, and we were going to let error minimization of the forces between the prediction equation and the open foam results help optimize those. So what we did was we said, all right, we're gonna do a least squares sum minimization of the error of the force difference between the model equation and open foam, our validated open foam model. And we found that the ratio of the wake width divided by the size of the neighboring structure, that's what these R numbers are, those came out to be around 1.2 to 1.1 and about 4 to 5.5 range, depending on whether you had the original flume width or the doubled flume width. And we wanted to pick something that were nice engineering values in terms of not being too many decimal places, but also encompass both of these results quite well, whether you have a wide or a skinny flume. And so we opted for just picking 2 values, which we'll show on the next slide. But I wanted to explain here first, before we go there and dive into a bunch of curves, how are we presenting these results? Well, each of these black points represents a case, a different configuration, and those are the actual open foam results. The dashed lines, the blue and the green and the purple, represent different factors. The green is going to be like the shielding factor. The blue is going to be the sort of the loss in the momentum factor, and the purple is going to be the channeling amplification of the force factor. And the red is the product of those 3, the total force factor. And so you can see our least squares minimization of the error is just trying to fit this red curve as best as it can through the black dots. And as you move away from the test structure, I showed you the one closest to it, the ones where the structures are essentially touching. As you move from the top left across to the right and then down to the next row and down to the next row, you're going farther and farther away. You can see, looking at the X position divided by the size of the neighboring structure, gets larger. And so as you go farther and farther away, you get more or less close to a uniform field. The wave has enough time to sort of reorder itself, and it's reduced in magnitude maybe, but it's not varying as much. And as you get closer, you can see the shielding really takes effect and reduces the force in the middle a lot. And these ones are using, like I said, we tried to find a sort of universal set of values that were sort of rounded off that fit both cases. And so instead of using either of the 2 more detailed values here, we settled for something in between. We picked 1.2 for the wake width amplification, and we picked 5 for the wake length factor. And also comparing the results for the doubled flume width using those same universal values for both, you can see the case matches quite well. In some instances, in the doubled one, you can see there are a lot of the open foam results. The black dots are below the curve. But that was not so concerning to us, because being above it, those points, is conservative in terms of predicting the force. So we let that go and said that was okay. The last thing I want to talk about is we compared our results also to a more realistic physical approximation, instead of coming up with these 3 factors sort of in an ad hoc fashion and then optimizing them. So this paper that I'm mentioning here, this dependence on square cylinder wake of dependence on Reynolds number from 2018, shows depending on the initial Reynolds number of the flow coming in, how big should you expect your wake to be. So instead of doing this parametric study to figure out how big our wake should be in our model, using these guys' equation, we tried to compare. And so they predicted for all ranges of flow, for all Reynolds numbers, equations that you can use to estimate the length of the flume in this image. And on here, they gave a similar figure for the width. And so taking those equations, you get the blue dashed line here to estimate the wake width and wake length factors and plug them into the equation. Whereas the red is the least squares error method from our parametric study. And you can see initially very close to the structure, they match quite well. But as you get farther away, the wake length is predicted to be very small by the Reynolds number only approach from the paper. And so you can see very quickly it goes to a perfectly horizontal line, which basically means there's no overlap or interaction of the wake with the design structure. Whereas in the actual open foam results, you're getting, there's still some interaction for much longer. So this case doesn't exactly match perfectly, but there's a lot more complexity going on here with the interaction between the two structures than there is in a model like this, where you're just taking one structure by itself. And so without further research, we're chalking that up to that. The interaction is causing this vast difference in the wake length. So overall, what did we come up with here? Well, we came up with these three factors: a momentum factor, a channeling factor, and a shielding factor, the product of which gives you a force amplification factor. And all of these can be estimated based on purely the geometry of your situation, which makes it very simple to figure out, what are your neighboring structures? What is your channel width before? What is your channel width after the neighboring structures? And estimate the force that way. We also showed that the open foam model was able to very well match experimental results and then be used for the parametric study to get this equation. And finally, using a purely Reynolds number based approach from analytical and numerical studies of a wide range for a rectangular structure, the results matched quite well in the near close separation of the structures, but as you got farther apart, the wake interaction was not captured well by that. So that requires some future work there. And in terms of our conclusions, what did we come up with? Well, we found that general channeling is going to result in increased demands due to increased flow velocities and depths, and this matches well with ASCE 7. However, shielding effects cause decreased structural demands due to flow redirection being not oriented at the structure anymore and velocity reductions. And this is not accounted for yet in the design code. We also demonstrated that using a code like OpenFOAM shows that CFD methods can very accurately replicate the experimental results of a tsunami-induced load scenario, even without an extremely fine mesh. So that's very beneficial for performing future parametric studies. And overall, the most important thing though was we came up with our modified design equation capable of predicting the force amplifications and reductions at the same time over a wide range of positions. And the last thing I'm going to say is what I think future work in this field could be, that would be good to do. This all was done for an elevated structure, so clearly this should be investigated for a non-elevated structure, something that goes all the way to the ground. And the other main thing that's a big problem here is the lack of a variation of the waveforms. You're not doing any sort of a probabilistic tsunami design scenario here. You're getting it to work for one wave, which is not terribly realistic in the grand scheme of things. And this is why I think in the future, the way to go forward is using reduced model order reduction techniques, which have already been done for tsunami inundations or things like blood flow in arteries, where you have very complex fluid dynamics that you can reduce down to simpler ones. The other thing you could do is you can do hybrid modeling, where you're going to take a shallow water equation and propagate everything right up to the structure on shore, and then do very small models for a range of initial conditions. Also, staggered positions of neighboring structures is important. Everything we did was just in rows, horizontally in the y direction. That's been shown by some people at OSU and other universities that has also a big impact on the flow redirection. So thank you for your attention, and I look forward to your questions.
Great, thank you so much, Andrew. Very informative webinar or presentation, and you had a lot of parameters to consolidate and organize in a easily understandable format. So thank you for that. At this time, we're transitioning to questions and answers. And we do have quite a few questions for you. The first one's going to be a comment first. The reason for ASCE 716 ignoring shielding effects. The structure providing the shielding might be removed in the future and therefore exposes the building to the full tsunami loads. This is similar to wind design where shielding is not credited, but channeling effects must be considered in the design of new structures.
Right, yeah, I've had this discussion with many people before, so I was expecting something like that.
Okay.
Thank you for your comment, though. Yeah, you're absolutely correct.
And I find that a follow-up question or follow-up comment that also tsunami loads apply both during incoming and outgoing flow. So although shielding might help during inflow, the building might still be exposed to drawdown loading. And that's an interesting comment because you've talked only about the incoming loading, right? You didn't study or present the
Right.
drawdown.
The conditions of our tests were not really amenable to studying the drawdown. We measured in our experiments values that you could call drawdown, but I don't believe I would say that the configuration of the flume beyond the structure was necessarily representative of a real sort of a coastline per se.
And are you able
so I'm not sure how valuable using that data would have been. We decided to only look at the initial impact.
Sure. Do the simulations provide an opportunity to consider that or evaluate that at all?
Absolutely. Now that we have a validated model, you could definitely go the extra mile and you could change your bathymetry a bit and you could see what the drawdown effect would be, yes.
Okay. And one last comment was that solid concrete blocks are a crude approximation of a true building. And so
right, we were just assuming they would be immovable, which actually was not true. We had to fasten them down with some extra restraints in the experiments. The waves could move them. But yeah, they were just meant to be geometrically, yeah, a crude representation of a building.
Okay. How is the impact force calculated in the numerical method?
How is the impact force calculated in the numerical method? So in OpenFOAM, what you're doing is you're just going to integrate all sort of traction stresses on a surface. So mostly it's going to be the pressure applied to the offshore and onshore faces, right? So the front and the back of the structure. There are viscous forces, but compared to the pressure in this scenario, you could almost neglect them and just take the pressure integrated over the front and back face, and that would give you the load. In OpenFOAM, though, when you ask it to record forces, generally you're going to do this over all the faces. So if there's shear stresses on the sides acting in the streamwise direction, in addition to the pressure on the front face and the back face, you're going to get those too. But yeah, the difference between with and without those is kind of minimal, at least in this regime of flow. In other regimes of flow at different Reynolds numbers and things, of course, you're going to see that matter, but not for these wave impacts.
And there was a follow-up question about elevated structures, but I think you mentioned that as a future rule, that it wasn't part of the scope of what you worked on.
Well, this was all elevated. The scope, we'd be backtracking to doing something that was not elevated.
Sorry, maybe I misunderstood the question.
There would be a big difference between, in this one, part of the flow can go under the structure, so the streamwise force would be lower. However, the elevated structures are going to get a larger uplift from the wave coming underneath them. So you get kind of a trade-off. You get a big uplift with the elevated structure and a lesser streamwise impact horizontal force, whereas if one goes all the way to the ground, you'd get a much larger overturning due to a larger horizontal impact force.
Okay. Another question is that RANS is basically used for estimation of mean pressures, but not the peak pressure. Can you comment on the use of RANS rather than LES?
Well, I guess the question is more, I think, how well do you really want to replicate local turbulence behavior which obviously LES is going to do a much better job of that than RANS. But I guess our point was, can we essentially get away with doing a much simpler model and still replicate experimental results in terms of the forces and the pressures? In terms of the numerical formulation, I can't honestly think of anything that I would remember that would say there's a big difference between what the pressure should be, whether you're using LES or RANS. Mostly you're just doing a much better job of getting turbulent flow resolved down to a smaller scale. So I'm not quite sure I understand the subtlety of the question there in terms of how the pressure should change.
Okay. Another question is, what could be some non-dimensional numbers that could be of interest in these simulations? Is there an analogy between wind simulations where people consider models that are reduced? And I'm not sure with how they're reduced specifically in the question, but maybe I can get somebody to follow up on it. Is that question clear to you, or are there non?
I think to answer the first part, I think is clear. I'm not totally sure about the second part. But in terms of the dimensionless numbers that would be most readily usable here, I think formulating something based off of the Froude number or the Reynolds number. Some researchers have already done this. I've seen this in some Japanese papers. They've tried to estimate inundation levels and demands using Froude number based equations. And that is something that has definitely come up within my circle of research people, but we haven't progressed to that yet. Our first thought was to just, what parameters do we have within our experimental conditions that we can play with to come up with an equation that would make sense, and that's what we use the geometry of our scenario to do that to start with. And later we could adapt it to being something more easily matchable with a more traditional dimensionless number instead of a wake width and a wake length dimensionless ratio.
Okay. How critical is the mesh refinement with respect to getting the force prediction correct? So, yeah, if you can comment on that.
I think in terms of getting the impact load due to the pressure on the front and back face of the structure, it does not seem to be that important. In all of my studies between both bridge models and these elevated structure models, that's what I've seen. The only reason you would really want to refine enough to see other effects is if you're really curious in terms of what are the boundary layer behavior going on the structure. But based on comparing to experimental results, it does not seem like you need to refine to that level to get the answers you're looking for. Even when you start varying the geometry of where the neighboring structures are placed quite significantly in terms of their location, near, far, left, right of the design structure, you're still getting good results. So I don't think it is as necessary unless you're concerned about downstream behavior where you want the wake of your design structure to be very accurate, then you would care. You need a lot of refinement there. But since we had no structures back there, we did not care.
Okay. And just one last question on the parameters of your study. Were things like the height of the tsunami, the water depth, the wave velocity, were any of those could you just recap the parameters that you were interested in and maybe comment on things that you might have wanted to also study?
Right. We would have loved to have studied a wide range of the broken waves, right, which all started as solitary waves, I believe. Our wave height for the solitary wave was something like 1.35 meters, and our depth of water in the deepest part was 2 meters, and it went down to something like 15 centimeters or 20 centimeters, something like that. So we would have loved to have varied these depths and also the beach slopes, and there's an endless number of things you can do, but we only had a very limited time of like 2 months, and I think we weren't sure how long we were going to get at the start. They told us much less time and we got more, so we ended up just moving the structures around more and exploring the shielding and channeling than varying the wave conditions, just so we had a wide range of geometries, but a minimal range of waves, or rather one real wave that was truly tsunami-like. So that was, I think, the biggest drawback of these results is you would need to do this again for multiple wave heights and initial water levels, as well as topographies.
Okay. Well, thank you. We are now at the conclusion of today's SimCenter webinar. On behalf of the attendees, Andrew, thank you very much for this great introduction to tsunami-induced loading of coastal structures. To the attendees, thank you for your questions. For additional upcoming NERI webinars, please check the SimCenter's website at simcenter.designsafe-ci.org. Check your inbox for emails from announce@designsafe that will have registration links for other events. And thank you for attending today's webinar.